This is another video in the series for Math 1224 for UTSA. We're going to be dealing with 3.2 trigonometric integrals. You can see that I've got the 6 common ones, or most basic ones, written down here. So sine of x dx equals negative cosine x plus c, integral of cosine x dx equals sine x plus c, and so forth. So you can see all 6 of them there. These you probably already know. If there's any that you don't know, you need to memorize these. So pause the video, write down the ones you're not totally solid on, and then write them down 10 times every day for the next week, because we really need to know them. Okay, so how about an example that's not just an antiderivative of a trig function, but some modification of a trig function? So integral of sine squared x dx. There may be other ways to deal with this one, but the way that seems easiest to me is to use a trig identity. So we're going to use the double angle formula for cosine. So cosine of 2x, or 2 theta if you want, equals 1 minus 2 sine squared of x. Oops, not theta, x. And all I have to do is solve for sine squared of x. So I will add sine squared x on both sides, and I'll also subtract cosine 2x on both sides in the same step, just to save myself a little bit of writing. And I get 2 sine squared x equals 1 minus cosine 2x. Okay, and then I can divide by 2 on both sides, so I get sine squared x equals 1/2 times 1 minus cosine 2x. Okay, and that's how I'm going to find this integral. So this equals, and I'll go ahead and put the 1/2 out front, the integral of 1 minus cosine of 2x dx. Okay, so now basically I'm just going to do the antiderivative term by term. I am going to need a substitution here, but I'm just going to sort of think, well, my inside function is a multiple of x, like kx. So my antiderivative, if I apply the substitution, I'm just going to have to borrow a 1/2 from somewhere, right? So this will end up being 1/2 sine of 2x. And I don't need to write out the substitution if I feel confident just doing it this way. So 1/2 times x minus 1/2 sine of 2x. Let's see. Okay, there we go. That is that antiderivative. Okay, how about the antiderivative of sine cubed of x dx? So this is a little bit similar in that I am going to use trig identities, but I need to use a different one. So what I'm going to do is I'm going to start by writing this as the integral of sine squared of x times sine of x dx. And it might not be at all obvious what I'm going to do, but I'm going to use one of the Pythagorean identities. I know that cosine of x squared, or rather cosine squared of x, I should say, plus sine squared of x equals 1, right? This is one of the most basic trig identities. If you don't remember any other trig identity, this is the one that is, I would say, the most essential. So I'll just subtract cosine squared x on both sides. So sine squared x equals 1 minus cosine squared x. Okay, and that's the replacement I'll make over here. So this is going to be the integral of 1 minus cosine squared x times sine x dx. Okay, and you might think, well, isn't this harder? We've made things more complicated, but it's actually going to work out really nicely. So now what I'm going to do is I'm going to distribute and have sine x plus sine x cosine squared x. And I think I'm not going to skip steps here. I could save myself a little bit of effort by doing 2 steps at once, but let's not do that in this case. At least for the first few examples, we'll try to avoid cutting corners. So all I did was distribute. Now what I'm going to do is I'm going to use the difference formula for antiderivatives and separate this into two integrals. So this will be the integral of sine x dx minus, and maybe you can tell why I'm doing this. If not, pause the video and think about, why are we separating these? Why don't we just do the antiderivative, term by term? So sine x times cosine squared x dx. Okay. Well, the reason I'm separating is that this term is pretty easy, just antiderivative of sine, negative cosine x, easy. The other term, this one, I'm going to have to do a substitution, right? I'm going to have to say And it might be, you might see what to do. I'm going to probably go with cosine, like u equals cosine of x, so that du equals negative sine of x, okay? And since this is not merely a, u equals kx, I'm going to write this out, just because this is not exactly the easiest substitution. And a lot of these problems in this section, we're going to need to do a substitution of this kind. And especially, we'll do more of that in the next section as well. So that's going to let me do this. I'll go ahead and do this one, negative cosine x, and then plus the integral cosine squared x times negative sine x dx. Okay, I'm grouping together so that I have u squared here and du there. So this is negative cosine x plus the integral of u squared du. Okay, so this will be negative cosine x plus 1/3 u cubed plus c, and then of course I can put u back in, or in other words, put the cosine back in. So negative cosine x plus 1/3 cosine cubed of x plus c. So there we go. That is the antiderivative of sine cubed of x. And if you want to check that this is correct, you can take that last step, find the derivative, and you ought to get, well, what you get, you know what, do we have room? Let's go ahead and do it. Let's, to illustrate what's going to happen. And you'll see. Okay, so let's do this. Let's do d dx of negative cosine x plus 1/3 cosine cubed x plus c, sure, whatever. It's going to be 0 anyway. So, and I don't have a lot of vertical space left, so I'll try to move horizontally. So, derivative of negative cosine x, well, that's sine x. It's easy, right? Plus, well, if I apply the power rule and the chain rule, this is going to be cosine squared x times negative sine of x, right? Plus 0, of course. You might say, okay, well, how is that sine cubed? We didn't get sine cubed, right? And you might see, oh, well, I know what to do here. Well, this is 1 minus sine squared x. So this is sine x plus 1 minus sine squared x times negative sine x. And when I distribute that, I get sine x, minus sine x plus sine cubed x. So I get sine cubed x. So we do have to use the Trigonometric Identity to convert it back and make it look like the original integrand. Okay, let's continue the pattern. We'll switch to cosine this time just to change it up a little bit. But what if we had the integral of cosine to the 4th x dx? So here's what we're going to do with this one. This one is, again, similar in that we're going to use an identity, but it is a little bit different. What I need to do is start by writing this as the integral of cosine squared x squared dx. Okay? Because I have an even power, I'm basically going to try to do the same trick before with the doubling of formula for cosine. Well, I say the doubling of formula for cosine. There's actually 3 of them. So previously we used cosine 2x equals 1 minus 2 sine squared x. So now we're going to use another one, cosine 2x equals 2 cosine squared x minus 1. Okay, so I can, I guess, add 1 to both sides. So 1 plus cosine 2x equals 2 cosine squared x, and then I can divide by 2 on both sides, so 1/2 1 plus cosine 2x equals cosine squared x. So now I can replace this part in the parentheses with 1/2 times 1 plus cosine 2x. So this equals 1/2 times 1 plus cosine of 2x squared dx. Okay. Now, if I distribute, well, let's do it this way. I haven't written the two factors out explicitly yet. So I'll go ahead and square the 1/2 and put it in front. So 1/4 times the integral of 1 plus cosine 2x times 1 plus cosine 2x dx, right? So this will be 1/4 times 1 plus 2 cosine 2x plus cosine squared 2x dx. I probably could have left this step out, but that's okay. I could have gone from here to here, but that's fine. Okay, so now what I need to do, well, this is easy, right? This is fine. It's like the one we did a moment ago. Now this one is still perhaps a little problematic. What I need to do is basically use this formula again. Basically, what I can do is rewrite this and use theta instead. Maybe that'll be a little bit clearer. Let's change colors here. 1/2 times 1 plus cosine of 2 theta, and theta can be anything, right? It's a variable, it can be literally anything. This is an identity. Well, theta, I can say, oh, well, I'm going to call theta, I'm going to call it theta 2x. Okay, so I'll have cosine of 2x squared, and I'll have a formula for that. So replace theta with 2x. So 1/2, 1 plus cosine, 2 times 2x is 4x. Cosine squared. This equals 1/4. And I'll do all the antiderivatives at the same time. I won't do the easy one first. Plus 2 cosine 2x plus 1/2 times 1 plus cosine 4x dx. And then before I do the antiderivative, one more thing, I'm going to distribute this 1/2. Well, I guess it's optional. Yeah, I'll go ahead and distribute it. That's fine. So I guess there's really 2 steps, not 1. So 1 plus 2 cosine 2x plus 1/2, because I can combine like terms at a certain point, plus 1/2 cosine 4x dx. Okay, combine like terms. We're almost at it. Well, we have room left. Maybe not a whole lot. We have room left. Okay, so 3/2. Plus 2 cosine 2x plus 1/2 cosine 4x dx. All right, so now everything is broken down into the easiest possible antiderivatives. I'm just using the antiderivative of a composite function where the inside function is kx. I'm borrowing a 2 or a 4, respectively. Or in other words, borrowing a 1/2 and a 1/4. So this is 1/4 times 3/2 x plus, well, I don't need to borrow 2, I already have it. So this is just sine of 2x. Plus, I need to borrow, because this 4, I'm going to have 1/8 sine of 4x plus c. And then if I want, I can distribute. I can say, okay, this is, was it 3/8 x plus 1/4 sine of 2x plus 1/32 sine of 4x. And probably if I really wanted to, plus c of course, probably if I really wanted to, I could go back and try to convert this back into having exponents. I have essentially angular velocities that are not 1, right? These trig functions cycle more quickly. The period is not 2 pi as a standard for a trig function, for a sinusoidal trig function. I could probably try to get it to look more like this by working backwards through these formulas. We're not going to do that. But if I wanted to, if I had a reason to do that, then I could. Okay, how about if we have both sine and cosine, right? So we have integral of sine x cosine x dx. No exponents yet. We'll get to that later. So there's at least two ways to do this. One way is to say that u equals sine of x. Another way, we could say that v equals cosine of x. And either one will work just fine. I'm going to go with cosine this time, just arbitrarily. So dv equals negative sine x dx. Okay? So I'm going to have to borrow in order to do my change of variable. So this is negative integral cosine x times negative sine x dx. Oops, sine x dx. Okay. So I've got v and dv. This is not to be confused, of course, with integration by parts. I'm just pointing out there are two different options, and I don't want to use the same letter twice for two different things. I could have gone with a and b, a equals sine x and b equals cosine x. It doesn't really matter which letters you use, just not x. So this will be a negative integral v dv, and then we'll get negative 1/2 v squared plus c. Okay, so then we get negative 1/2 cosine squared x plus c. Now, if you work this out the other way, then you're going to get what appears to be a different result. But that's basically the plus c takes care of that. If I go ahead and do that in a different color, let's say du equals cosine x dx. Then when I go to do my substitution, I don't have to do any borrowing. I already have u and du ready to go. So it's actually a little bit easier. So this is the integral of u du. So I get 1/2 u squared plus c. So I get 1/2 sine squared x plus c. And you might go, hey, those definitely look different. How's it possible that I'm getting two different answers? And or how is it possible that these are the same thing, right? Well, if you think about it, sine squared plus cosine squared is 1, so their sum is a number, right? So the difference in the two antiderivatives will also be some number, right? So if I do this, I say, well, if I say 1/2 sine squared, and you know what? Let's well, yeah, let's do this. Sine x plus c1. Let's call that. Well, c2 rather, since I did come up with this one second, and this one over here we'll call c1 because well, they appear to be different. So does this equal 1/2, or rather negative 1/2 cosine squared x plus c1, right? Are those the same thing? Are they equivalent? Well, if I double everything, that's gonna get rid of fractions. So sine squared x plus 2c2 equals question mark negative cosine squared x plus 2c1 question mark. And if I add cosine squared to both sides, I get cosine squared x plus sine squared x plus 2c2 equals question mark 2c1. Well, this is 1. So 1 plus 2c2 equals question mark 2c1. So basically what this means is that if you were to decide, for a particular problem, that C2 is like, I don't know, 8 or something, then you could plug in 8 and find out what C1 would have to be to give you the same equivalent answer. But they are equivalent, and that's because of the way sine and cosine behave. Sine squared is negative cosine squared plus something, plus 1 in particular, right? So these are the same result, although they look different. Okay, so one thing you're going to want to watch out for, in the web work assignments, the answers should take this. They should tolerate this if the problem is programmed to accept this. it should accept that as well. There's a I forget what should I call it. There is a it's part of the answer checking system where you can tell it that plus C is part of it, and it will check to see if your answer differs from the internal answer by a constant. Then it goes, oh yeah, that's equivalent. It knows what an antiderivative is basically. So don't worry too much about that. If there's more than one correct answer, more than one way to do the problem, for the antiderivatives, WebWorks should handle them just fine. Okay, how about this one where we have sine and cosine, but there are exponents. So now this is where things start to get a little bit trickier. And as before, I said there's probably more than one way to do this, but I think I'm going to show you what I think is the easiest way. So I'm going to look at the two exponents and notice that one is odd and one is even. And I'm going to focus on the odd one. I'm going to peel off one copy of sine and pair it with dx. Okay, so I'm going to write this as sine, or sorry, rather integral sine squared x cosine squared x times sine x dx. Okay, and this is going to be my dv, sine x dx. So I'm going to say, oh, well, that means that v needs to be cosine, or if I want negative cosine, whichever, it's going to work out anyway. So dv equals negative sine x dx. Okay, and what I'm going to do is, you might say, okay, that's cool. We'll borrow minus. This is handle. This is dv. This is v squared. But what about this guy? What do we do? How are we going to handle that? Well, all I got to do is use the Pythagorean identity. If v equals cosine x, then I can just replace sine squared of x with 1 minus cosine squared of x and then put v in. So this is going to be negative because I'm borrowing a minus sign to put with dv. 1 minus cosine squared x, that's Pythagorean identity, times cosine squared x times negative sine x dx. So I get negative integral 1 minus v squared times v squared dv. Now I've turned this into a relatively easy antiderivative using just power functions. So I'll distribute the v squared to negative integral. Well, I could absorb this minus in there. Let's go ahead and do that. Let's do that. So this is the integral of v squared minus 1 v squared dv, which is then the integral of v to the fourth minus v squared dv. So this is going to be 1/5 v to the fifth minus 1/3 v cubed plus c, and then we can put cosine back in. So 1/5 cosine fifth power x minus 1/3 cosine cubed x plus c. And I'll reiterate, there's probably more than one way to do this, but I think this is probably the easiest way. Okay, what about this, where both of the exponents are odd, right? Well, I'm going to do a similar thing, but I'm going to focus on the lesser odd exponent. I don't want to use the larger one. That makes it harder. You can do it. It will work, but it makes the problem harder, so let's not do that. So I'm going to peel off one copy of cosine and pair it with dx to make my dv. So this equals integral sine 5x times cosine squared of x times cosine x dx. Okay, so if dv is going to be cosine x dx, that means that v needs to be sine x. The dv equals cosine of x dx. So that means that this is dv. That's settled. I'm going to replace the sine to the fifth power of x. And then, well, what about the cosine? Well, again, we're going to use the Pythagorean identity. I'm going to replace that with 1 minus sine squared of x. So I get the integral of sine to the fifth power of x times 1 minus sine squared of x times cosine x dx. Now I'll do my replacements as an integral of v to the fifth power times 1 minus v squared dv. So this is the integral of v to the 5th power minus v to the 7th power dv, right? I'm just distributing. So this is 1/6 v to the 6th minus 1/8 v to the 8th plus c, and then I can put sine back in. So this is 1/6 sine raised to the 6th power of x minus 1/8 times sine. Okay, and that's basically how to do this one. And again, there's probably another way to do that. We could peel off from the other one. Like we could have used v equals cosine and dv equals sine or negative sine dx, but that would be overly complicated. Okay, what about if we have sine and cosine and the exponents are both even? If we peel one off, we're not going to be able to do any switching. So that's really not going to work if we try to do that. So instead, we basically have to deal with the way that we did with sine squared of x. We say, well, let me use the double angle formula for cosine. So this is going to equal the integral of 1/2 times 1 minus cosine of 2x times 1/2 times 1 plus cosine of 2x dx. Okay, and then from there I'm going to FOIL. I'll put the 1/4 out in front. So 1/4 times 1. Conveniently, this is a 1 minus a times 1 plus a. Right, so I get to cut corners a little bit. I know that the a and minus a will cancel. So this is 1 minus cosine squared of 2x dx. And I get to use the double angle formula for cosine again. So this would be 1/4 times the integral of 1 minus, so this would be 1/2 of 1 plus cosine 4x, close parenthesis, dx. Okay, so then I can distribute the 1/4 if I want, but I'll leave it where it is, and then this 1/2 I can distribute. So 1/4 times 1 minus 1/2 minus 1/2 cosine 4x dx, and I can combine like terms. So 1/4. I'm going to distribute while I'm doing this. So this will be 1 minus 1/2 is 1/2 times 1/4 is 1/8 minus 1/8 cosine 4x dx. So this equals 1/8 x minus 1/32 sine of 4x plus c. So in some ways that's easier, but so far we've been using a lot of Trigonometric Identities, and that's how most of these are going to go. Okay, so here's one that we've seen before, and I used to think there were only 2 ways to do this one, but there's at least 3. I thought of a third way of doing this one recently, but I'm just going to pick one of the straightforward ones. So, well, maybe we should list all 3. So let's say we could do u equals tangent x. We could do v equals secant x, not secant, sorry. Yeah, secant x, yes. And then I believe also we could do, let's say w equals cosine x. I believe that would work as well if we wanted, yeah, that would work. So I don't want to do this way because basically this example done with either one of these will lead into later examples. So we're not going to do that third way. So I'm going to do, let's do this one. So u equals, well, you know what? Let's do this one. This one's maybe more straightforward. So let's do secant. So that means dv equals secant x tangent x dx. Okay, so I need to peel off one of these secants and borrow it and use it to pair with tangent to make dv. So this is secant x times secant x tangent x dx. Okay, so this is going to be an integral of v dv, so 1/2 b squared plus c. So this will be 1/2 secant squared x plus c. And as I said, if we wanted, we could do this with tangent instead. And much like with sine and cosine, probably we would get a different looking but equivalent result. Okay, so now this one's going to be a little bit harder because we have bigger exponents involved. So one thing we could do is say, well, let's try using tangent. Let's just see how that goes. So if we do u equals tangent of x, then du, of course, equals secant squared of x dx. I need to peel off a secant squared to pair with dx to make du rather. So this would be the integral secant seventh power of x times tangent fifth power of x times secant squared, and we'll put this in parentheses even, secant squared x dx. Okay, so what we get is this. Here's dv, and here's du. Sorry. And here's u to the fifth power. What about this guy? Because this is an odd exponent. I can't use a Pythagorean identity. I could try to use 1 plus tangent squared x equals secant squared x. But I don't have an even number of factors of secant. So I kind of get stuck and this doesn't work. So let's try using secant for the substitution instead and see how that goes. So I rewrite the problem. Integral secant 9th of x tangent 5th of x dx. And then we'll say that v equals secant x. So that dv equals secant x tangent x dx. So now I'm going to peel off one from each of secant and tangent, which will mean what's left over will be even exponents. Okay, so this will equal the integral of secant to the 8th x times tangent 4th x times secant x tangent x dx. So here is dv, right? Here is v to the 8th power. And here, what I need to do is write this as tangent squared in parentheses squared. And then I can use the Pythagorean identity to replace tangent with secant. So this is integral secant 8x. And notice that I'm just going to switch over to v all at once. It's improper to take some terms and turn them into the other variable and then do others later. You should just do them all at the same time. Okay, so this will be integral secant 8x of tangent squared is secant squared minus 1. Squared, of course, times secant x tangent x dx. Okay, so now I get v to the 8th power times v squared minus 1 squared dv. Okay, so now I can do some distribution. So I get v to the 8th power, v to the 4th minus 2v squared plus 1 dv. So I get integral v to the 12th power minus 2v to the 10th power plus v to the 8th power dv. Now I can do antiderivative, so 1 over 13 v to the 13th power minus 2 over 11 v to the 11th power plus 1 over 9 v to the 9th power plus c. And then I can plug, what was it? Secant? Plug secant back in. So 1 over 13 secant the 13th power of x minus 2 over 11 secant 11th power of x plus 1 over 9 secant the 9th power of x plus c. So that one's somewhat complicated, but that's it's a complicated problem that we started with. The integrand, rather, was complicated. Okay, so what about if we have secant with an exponent, but we don't have a tangent to balance it with and borrow pieces? How do we handle that? Well, we kind of get started the same way, except it's not clear at the beginning what substitution we're going to do. So this one, I think it's best to just explain by showing. So I'm going to start with our common trick of peeling off one copy of the trig function. So we got secant squared x times secant x dx. Okay. Now I'm going to replace secant squared with 1 plus tangent squared. So this is the integral 1 plus tangent squared, which is not quite what we were doing before. Previously, we would have secant and tangent, and we'd try to get it in terms all of in secant or all of in tangent. Now we're doing the reverse. That's because, well, you'll see. So secant x dx. So now if I distribute this, I'll have the integral of secant x plus tangent squared x secant x dx. And now, hey, we've got a tangent to work with, to balance the components with, right? Well, we'll see about that. This is one that is typically covered in Cal 1. Maybe you recall, maybe not, so I'll quote it here. So the antiderivative of secant of x dx, this is the natural log of the absolute value of secant x plus tangent x. C, of course. So as I said, this is typically covered in Cal 1. And if I can make a separate video or something if anyone requests it for this one. So this is, I'll separate these two. So this is the integral secant x dx, which we will replace with the logarithm in a moment, plus the integral tangent squared x secant x dx. So now again, we need to think, okay, what am I going to do to get the ball rolling on this? And if we try to do identities, this is how we got here by doing identities. So we started with that. So we start with if we try to do substitution, it turns out it's not going to work. You can try it, and you probably should try it. Try to solve this one through substitution. I'll tell you, it's not going to work, but it's something you should try. But in the interest of time, we won't do that here. Next is integration by parts. Okay, so that's what we're going to have to do for this one. So there may be more than one correct or workable way to do this. I'm going to choose to do it in the following way. I'll go ahead and just say what this one is. Well, let's save room, and we'll do this one at the end because we are going to be strapped for horizontal room. So we're going to say that this is the integral of tangent x times secant x tangent x dx. And I'm going to say that this is my u, and this is my dv for integration by parts. Okay, so du is, of course, going to be secant squared x dx, and then v is going to be secant of x plus c, but we don't need to do that in this case. It would end up kind of balancing out anyway. So equals integral secant x dx plus, well, u times v, so tangent x secant x minus the integral, well, v du. So secant x times secant squared x dx. Let me rewrite this and see what we've got here. So the integral of secant x And some of you might be picking up on what's going on with this. Tangent x secant x minus integral secant cubed x dx. And there's, I guess there's three responses. One response is, okay, what now? Another response is, oh man, this is terrible. This is what we started with. We haven't gotten anywhere, right? And the third response is, oh, that's great. That works out really nicely. So because I have this minus here, I can do the following. I'm going to move this over a bit. No, caught the line above it. Move this over a bit and say, okay, this is an integral secant cubed x dx equals all this. So I can add, the integral of secant cubed x dx to both sides. So I get 2 integral of secant cubed x dx equals the integral of secant x dx, which we know that from Cal 1, plus tangent x secant x. And at this point, I'll put plus c. And then I can divide by 2 on both. So, well, I'll do the 2 in a moment. I'll go ahead and say, oh, well, this is ln, right? This is natural logarithm. The absolute value of secant x plus tangent x plus tangent x secant x plus c. And then if I divide both sides by 2, I'll get the integral of secant cubed x dx equals 1/2 ln of the absolute value of secant x plus tangent x plus secant, tangent. The order doesn't really matter. Tangent times secant or secant times tangent. So tangent x secant x plus c. It's only in that order because that's what I got from the integration by parts, and I was maintaining the u v order. So there we, oh, I forgot something. Pause the video and look. What did I forget? The 1/2. Okay. And some of you might be thinking, well, why doesn't the c get a 1/2? Well, c is a constant. It's some number we don't know, and for this problem, we don't need to know. So half of some number that you don't know is just some other number you don't know. So I'm not going to worry about labeling it differently. Okay, so what if we had something like sine of 3x times cosine of 5x? Well, we're going to have to use another trig identity, but this is a little bit one that's a little bit more complicated. This is called a product to sum formula. I'll put a link in the video description to another short video talking about the different formulas. That video doesn't prove them. They're not that difficult to prove, but they are tedious. So that video does not go through the effort of proving them. So if you have something like sine of alpha times cosine of beta, okay, this is going to equal 1/2 times sine of alpha plus beta plus sine of alpha minus beta. And alpha and beta can be anything. This is an identity. So alpha could be, say, 3x, and beta could be 5x. So this equals the integral of 1/2 times sine of 8x, right? The sum of the two arguments, plus sine of negative 2x, 3x minus 5x dx. Okay, so this will be, if I simplify a little bit, I'll put the 1/2 out in front. And what I'll do is, since sine is an odd function, this minus sign can come out front as well. So minus sine of 2x. If I really wanted to, I could use the double angle formula for sine, but that really won't help me. These missing parentheses there. These are easy substitutions, so more trig identities will not make the problem easier. If anything, I'll make it harder and more steps involved. So 1/2 times 1/8 cosine, negative 1/8 rather, cosine of 8x plus 1/2 cosine 2x plus c. And if I want, I can distribute the 1/2. So negative 1 over 16 cosine of 8x plus 1/4 cosine of 2x. Let's see, of course. Okay, let's find the length of the curve y equals ln of cosine x on the interval pi over 4 to pi over 3. So the integral will be pi over 4, pi over 3 of the square root of 1 plus dy dx squared dx. Okay, so dy dx equals, well, the derivative of the outside function will be 1 over the inside function times the derivative of the inside function, and we'll get negative tangent x from that. Okay, so basically, if you square that, right, dy over dx squared, well, we'll just have tangent squared. And if you add 1 to that, right, we get secant squared x because of the Pythagorean identity, tangent squared x plus 1 equals secant squared x. So this equals the integral from pi over 4 to pi over 3 with the square root of secant squared of x. This is something we probably could have done earlier in an earlier video, but it fits nicely here because of the frequency of the usage of trig identities. So since we're in quadrant 1 with our interval, pi over 4 to pi over 3, everything is positive. All the trig functions are positive. So when you have the square root of a square, you have to be careful. Oh, do I have a plus? Do I have a minus? Which quadrant am I in? But in quadrant 1, everything's positive. So this is just the integral from pi over 4 to pi over 3 of secant x, which we used in a recent example. So this will be the natural logarithm of the absolute value of secant x plus tangent x evaluated at pi over 4 and pi over 3. And I'll point out also that we don't really need absolute value here. I could just as well use parentheses because everything's positive in quadrant 1 anyway. So this is going to be ln, I guess I'll drop the parentheses here, ln of secant of pi over 3 plus tangent of pi over 3 minus ln of secant of pi over 4 plus tangent pi over 4. So if I want, I have a difference of two logarithms, right? If you have ln a minus ln b, you can write that as ln of a over b. Let's go ahead and do that. So this is ln of big fraction, and the first argument will go on top. And let's see, so secant of pi over 3, that's going to be, what will that be, 2? So 2 plus tangent of pi over 3, that's root 3, right? Secant of pi over 4, that's 2 over root 2, so that's root 2. And then tangent of pi over 4, that's a 1. So there we go. That is the arc length. You know, oftentimes we'll want a decimal approximation because you could ask, well, yeah, but how much is that? Is that a lot or not very much? And the exact value, it's often not very clear. Is that a small amount or a large amount? So let's type this in a calculator and get a decimal approximation as well. I get about 0.436. So no, it's pretty short, but from pi over 3 to pi over 4, that kind of makes sense.